So let's talk about heaps. Now I'm used to a structure used by operating systems called the heap, which I mentioned before, but this is a different thing. This is a structure defined in computer science, and apparently they misuse the word heaps, or maybe there's some connection, I don't know. But anyway, it's a specialization of a tree where the nodes are ordered. So either the root is the maximum or the root is the minimum. So a max heap, not just the root, but every parent node is greater than or equal to all its children. That's what you have here. So notice here, they're not necessarily in order. Here you have 28 to the right of 32, but the only thing that matters is these children have to all be less than their parent. So that's a max heap. And a min heap, of course, is just the opposite. Every parent is less than or equal to all its children. And again, there's no particular need for the children to be in any order. Here you have 20 and 28, and over here you have 45 and 30. All right. So a binary tree, we talked about before. A binary tree is one where every parent has no more than 2 children, 0, 1, or 2. It's pretty interesting. This is actually, we'll get to this later in sorting, but I actually got a big promotion at my job years ago because there was a problem where we had to find the one letter that was wrong out of 1,200 printed letters. And I just happened to have read a computer science book or something like that that said that people naturally sort things into 5 categories like your fingers. So that's what I did. Instead of making a binary tree, I made a tree that sorted into 5 groups and then 5 subgroups to be the fastest for human to sort those 1,200 letters. And we were able, in a few hours, to sort 1,200 letters and find the one that was wrong. By doing this, by reporting it into groups, and then 4 of the groups will be right and 1 will be wrong, so the problem gets smaller. And we had basically a log time solution. And my boss was very amazed because he didn't know that. He thought the only way to find it would be to go through all 1,200 one by one, comparing them to a list of what was right. And he said, we'll never get it done in time. And he didn't understand the value of binary tree. Anyway, that was a 5-way tree, if there is such a word, where you split it 5 ways each time to fit human psychology, but in computers, you usually use a binary tree. So each decision is just a yes or a no. All right, so now you've got index positions. And so if you have a full tree, which they call, I think, a complete tree. And a complete tree is one where you fill every row before you start the next. So that would be something where you try to have the minimum number of levels. And therefore, the left child is going to be at index 2n. So here you're at 1, here's 2, 3, this is going to be 4, next one's going to be 8, 16, and so on. This is going to 8 and I think 2 to the n, actually, not just 2n, but I think 2 to the n. I think this should be a superscript. I think that's right. It's going to be, because each one of these is twice as big. So which is going to matter a lot to us later when we calculate the computational efficiency of this. Each level is twice as big as the one above it, and that means each level has more in it than all the levels above it put together. All right, so, and therefore we're going to start counting at 1 for this to be true. Therefore, if we make it a list in Python, we'll have an extra element at 0, which we just ignore. Due to computer science's very strange policy of starting to count at 0. When I first learned computer programming in like 1973, we used a language called BASIC that started counting at 1, and that was a whole lot easier for humans to understand. I think it was a mistake to switch to this starting at 0, but that's where we are. All right, so if you want to insert into a heap, you insert at the end, where it's easy to insert something, and then you heapify. You rearrange things so that it obeys the heap property again. Those are the 2 steps. So you insert. Now this is heapifying. You compare it to its parent and swap if necessary. Now this looks like a min heap, 3, 5, 5, 7, 9. So 2 needs to move up because 2 is smaller than 6, and you want the smallest thing on top. All right.
Would 2 move up to the top?
You don't move right up to the top. You just compare it to its parent. That's how they do heapifying. It will have another stage later where you compare it. So you do it 1 step at a time. You could possibly try to guess 2 or 3 hops at a time, but that's never done because this turns out to be very efficient. We will get to that later in the sorting chapter. There's one where you actually do try to guess where it is and go there instead of just splitting it half and half and half. And that can be more efficient for searching a list, but for this binary tree,
I didn't mean like in 1 step. I meant like first do that and then
Oh, yeah, it'll percolate to the top, absolutely. It'll percolate. So after you flip the first one, then you repeat it again, and you keep going until it doesn't fail the test. So it will take 2 hops to get to the top, and therefore its complexity is log n, because you only had to do one side, and that's going to be the log base 2 of the number of elements. So it's very fast. So here we're going to build a heap, and when you build a heap, you just keep inserting values. You have to keep reheapifying every time. So here we insert 4, it's alone, so it sits there all by itself. Then you add 8. Well, we're making a min heap, so it's fine that 8 is a child of 4. Then we insert 7, and again, no correction is needed. Then we insert 2. 2 is going to have to do hop, hop, get to the top. Then we insert 7, and it's okay here. Then we insert 9, which is okay down there. And then we insert 10, which is okay down there. So in this case, we only had to make changes in one level of heapifying, but we did have to do at least one comparison operation every time to verify that the heap property was not being violated. Then we insert some more. We insert 5 here. It's going to have to make 1 hop up. Insert 1. That's going to have to hop 3 times to get to the top. And you insert 3. 3 is going to start here, and it's going to have to make 1 hop up because the number its parent is 4. So that shows how it goes. You have one insert operation, which is constant time, and then you have one heapify operation, which appears to be log n, although as we're going to see, it's not really. So here's the last step where we insert a 6. Insert a 6 here, it's going to flip at the 9 and go in there. So that's the game. And here's the Python code for it, which is pretty obvious. This part down here gets a little confusing. If self-heap k is less than self-heap k / 2, this is how you can refer to the parent by dividing by 2. Then you know how to, then you can interchange them. And this is kind of cute. I wasn't able to do this in more primitive languages. If you're going to flip 2 items, you can put AB equals BA, which is nice. I was so used for 50 years having to do X equals A equals B equals X, have an intermediate value. Python lets you do it all in one step. All right, let me take a look and see if there are comments in the Twitch. Okay, nothing, fair enough. Okay, so the code to build a heap from the last 2 slides is here. So I'm going to have to do this now. It appears to be n log n. I had to perform this insert operation n times for these n elements, and each one of them then had to be followed by what appeared to be log n steps to heapify. But I invite you to notice something, which is that almost none of them actually did any heapifying. If you look at it, this one did, almost none of them actually involved any flips, and that's going to turn out to change the statistics quite a bit. All right, but this would be a upper bound, would be n log n. It's, all right. And the resulting list, by the way, is not necessarily sorted, not completely. It just has the heap property. The parents are smaller than the children, but as you can see, they're not really in order if you read them this way, 3, 6, 10, 7. They have a certain order, but they do not have a simple order the way they would if you were sorting a list. All right, now we can talk about the complexity. You do n inserts. After each one, you heapify, so you get n log n, and that is a correct upper bound, but it is in fact unnecessarily pessimistic. It really will not take that long in practice, and I found a fun video from either MIT or Stanford where they explained this. The point is most nodes stay near the bottom of the tree, and that's what I was pointing out back here. Because of the structure of this tree, the bottom layers contain far more nodes than the upper layers. So almost all the work is done down here. You very rarely go to the upper layers at all. So it turns out that it's actually order 1 to heapify from the bottom. It usually takes, it doesn't matter how big the tree is, because the bottom layer keeps getting bigger and bigger. So the majority of the work is always done at the bottom. You very rarely have to go to the top. So in practice, it's really order of n, not order of n log n. That's right, it looks like a pyramid. See, in order for this logic to work, you wouldn't want a pyramid, you'd want a square. If every level was the same, then you'd have to do log n steps every time. But here, it keeps getting smaller and smaller in a factorial way at each level. So if you add up all the steps, you get a total amount of work in the loop is 1/4 of the time you make 1 step, 1/8 of the time you make 2 steps, 1/16 of the time you make 3 steps, and so on, just because there's less and less nodes up there. So even though this term in parentheses grows linearly, the other term shrinks quadratically. So for large n, only the first term survives. The total work involved is just order of n. The heapifying is effectively independent of size. So that's pretty cute. And that's because even if the bottom gets much larger, which means you're more likely to find your answer there, but also you only have to do one comparison no matter how big the bottom is. So anyway, that's an interesting detail. It actually only implied in your book, which I found kind of interesting. Your book made the claim that it was order of n, and I said, why? So I looked it up, and that led me to this lecture. All right, see, this is, all right, that'll have to wait. All right, so now if you want to delete things, usually you end up deleting the root, because the more common reason you delete is to get the list really sorted, not just this strange heap property, which isn't exactly a sort. So if you delete the root, then you take the last element and move it to the root, so now at least your tree has the right structure, and then you're going to have to heapify from the top. If you heapify from the top, you're going to have to consider whether the top should move down, and then consider whether it should move down again and move down again. And that means you're heapifying from the top, so you're not going to enjoy that efficiency that we talked about heapifying from the bottom. So if you delete at the root node, pardon me, not code, but node, all right, that'll shrink the heap by 1. Here's the code that does it. You delete the root, shrink it by 1, pop, and then put the item on top, and then sync is what's going to heapify from the top, where it's going to start at the root node and see if it needs to move, and then test every place it goes down the steps to see if it has to move. So here's one that builds the heap by just inserting all these numbers one by one, then prints it. Then I'm going to delete at the root and print it again. So here's the heap. 0, its children are 2 and 3, and the children of 2 are 5 and 7, and the children of 3 are 9 and 10, and so on. Then we'll delete at the root, which should delete it deletes 2, which in fact confuses me. Oh, I see. Why? Oh, the 0. Remember we talked about this. The 0 doesn't count. The 0 is that dummy element at the start to just use up element 0. It all starts here. So the root is actually 2. So after we delete it, of course, you get the tree like this, where every node, its children are larger than the node. And here, this is a min heap. All right, so that's what it's going to look like. Now, you could possibly want to delete from somewhere in the middle of a heap. That's not too obvious why you'd want to do this. But if you wanted to do this, you delete whichever node it is, and you take the last node and put it there, and then heapify is the logical way to do it. All right. Now, heapifying, you compare the root node to a child below it. First, all right, you compare to children. Then you compare to their children. So this is heapifying from the root. If you delete from a specific location in the middle here, first you'd have to compare to the root to see if it moves to the root. Then we're going to have to compare it to both children to move it down. All right. So after a swap, we move it down here, and then we're going to compare it to the children again. That's pretty obvious how to do it. So a heap sort, it turns out to be efficient for very large tables of data. You create a min heap, then you read and delete the root node and heapify, and just keep doing that until you get all the elements. And you're taking advantage of these log steps. So building the heap is order n. Deleting the root occurs n times. Each time you heapify from the root, and this time it really is log n, because the root is very likely to percolate to the bottom, where most of the nodes are. So that's really going to take log n times. That's why heapifying from the bottom is much more efficient than heapifying from the top. All right, and so one object you can build with these things is priority queues. And priority queues, I know I'm familiar with them from network traffic, and there are a lot of places where you have a list of items and you don't want to just serve them in, first out, or last in, first out. You have some other consideration for which one you should serve first. There's a priority number, and you want to serve the highest priority items first and then the lowest priority items. This is really important for voice over IP. You may not know this, but over the last decade or two, almost all telephones have moved from analog service to digital service, and they've moved to digital service over shared trunk lines, which include now, normal telephone trunk line contains multiple phone calls on the same line, But now we have trunk lines that share digital data with telephone data. So you have people downloading web pages and email on the same wire as their telephones. And the problem is, if your email takes an extra 100 milliseconds to arrive, you don't notice or care. But if there's a gap in a stream of packets to make a voice, people will notice that even down to like 10 or 20 milliseconds. So you have to put a higher priority on the voice over IP packets so they always go through first, even if other packets have to wait for them. And this is a pretty common problem. All right, so here, CPU scheduling is another one where you're going to consider different jobs in your machine and they're each going to get their turn at the CPU. You may have a higher priority job, one over another there. And just the shortest path we talked about a while ago, I'm not quite sure how it works. Here's an H-star algorithm, another one. And Huffman codes for data compression. These are ones where you take large blocks of data and encode them with smaller blocks of data to make them smaller, the way old telegraph codes worked. And they're listed in your book as examples of priority queue, although I'm not sure I completely understand why these work. Here it's clearly true. Their CPU has certain jobs that have to be done right away, and other jobs that can wait. All right. Anyway, so your priority queue, if the numbers represent the priorities, then you can NQ here. When you NQ it, instead of just, you're going to have to put it in its correct place and order. You don't just put it in the front, because you're doing last in, first out, and you don't just put it at the back because you're doing first in, first out. You put it at its order in the queue by priority. And I think an example of this I know is you go to the deli counter at the grocery store or my doctor's office, thank God, you don't have to stand in line. You get a number with a ticket on it. With the ticket with a number on it, and you can watch a board and see when your number comes up, which is much better than making people wait in line, which is ridiculous. All right, so to create this, you NQ elements from this end and DQ them from this end based on the priority. So the higher priority comes out first, the lower priority comes out next. And so when you NQ a number like 6, you don't put it at the end, you put it where it belongs. So that should be pretty obvious. Let's take a look at a Kahoot. Let me see if there's comments in the Twitch, and there aren't. All right. This is the chapter 6, right? Chapter 7, all right. There's 7, all right. Make sure the Twitch is seeing the right thing. And they are. Okay, good. All right. My camera's left off from the last class, so I need to save some of the screen. All right. Like we got everybody that's coming. All right, so which data structure places the items in a sorted list? that's interesting. I was going to argue for none. Priority queue is sorted by priority, not by data elements, so I'm not sure this is as brilliant a question as I thought when I wrote it. You could argue for that. I think this might be the best answer. Oh, it is. Oh, good. Now I feel better. For a minute, I thought it was rating you correct for priority queue. The priority queue is not sorted by the elements, not sorted by the stored data. So none of these are in order by the stored data.
So I thought I just meant sorted as in numerically in general. Like,
Yeah.
there's a lot of different ways you can sort a list.
Well, yeah, but what you normally mean is you sort by the data that's stored and you make it either ascending or descending. And none of these have that property. The priority queue sorts by something else. So, I mean, you could argue that this is sorted, but it's not sorted by the data. I think it's making a more careful statement in the question would improve this. Sorted by the data elements that are included.
It's kind of interesting you thought priority queue was correct just because so many people answered it.
Oh, well. That's communism. Anyway, all right. Yeah, but you could be right. Anyway, I can't change it now, but yeah, I'd rather rephrase the question. Anyway, that's part of why these things are extra credit. They're not necessarily totally fair. And by the way, if you find mistakes in the quizzes that are graded, let me know. I've found a couple of mistakes in there, so let me know. All right. All right, which data structure fills each row before starting the next one? That's a complete binary tree. That's what makes it complete. You completely fill each row before you go to the next one. Not just an arbitrary binary tree. And certainly not necessarily a heap. A heap doesn't even need to be binary. It can have more than two children in principle. All right. All right, so which one of these is order of log n? Yeah, remember, the heapifying from the root is where you actually have to do log n steps. Heapifying from the bottom is order of 1. Building a heap is order of n. And deleting from a heap is order of n log n. Because you build from the bottom, and therefore heapify from the bottom, and you delete from the top, and therefore heapify from the top. All right, so that's good. This is